In this video, in this video series, I want to discuss Maxwell's correction to Ampere's law. So in general undergraduate electricity and magnetism class, or say an AP Physics class, you'll probably learn Maxwell's four equations. And I think the most notable one, and the one that is most surprising at first, is that there's a correction to Ampere's law. So all the other laws look pretty similar to what you learned them initially, when you learned them separately as Gauss's law, or Gauss's law for magnetic fields or whatever, or Faraday's law. You learn them and they seem to be the same inside Maxwell's laws, four laws of electromagnetism. However, there is this correction term where in the first case we learned it as the total integral, so the closing integral of the B field dot dl is equal to mu naught times the current enclosed. And in this case, where we have this extra term that I'll discuss soon. But first, I want to go over exactly what Ampere's law is so that we're all on the same page before we dive into the correction for Ampere's law. So here I have a simple setup of a infinitely long wire, and there's a current running this way. And the question is, and I encourage you to pause the video to actually answer this question, what is the magnetic field from this wire, right? So pause the video and think about it. And then I also want you to answer, at a given r distance away, what is the magnetic field? Is it the same as if it's any r distance away? So if it's like here and here, the magnetic field is the same? Yes or no? If there is a difference, can you explain why? If there is not a difference, can you explain why? So if you've tried it, I will now reveal what I am going to say. So in this case, we want to use the right hand rule, and it might seem a little bit weird, and I'm not sure if everyone has learned this, but the right hand rule is simply a human convenience, right? So we have these observations from these scientists in the past who discovered that current running this way, and using the right hand rule, we will see that the magnetic field generated is as such, where dots meaning that the magnetic field is pointing outwards of the page, and X's meaning it's going into the page. And the right hand rule isn't saying that like we just made up this stuff, but it's more of saying that we have an observation in the real world, and the right hand rule just so happens to be something that could be used as a simple crutch to represent what's happening. And fundamentally, it's because we can represent three dimensions in our right hand, right? So the thumb pointing in one direction, and then the curling motion of the fingers produces three dimensions, which happens to correlate with what's going on in the real world. I just wanted to give that spiel just in case anyone has not actually thought about that, but I thought it was interesting. So anyways, the question is now, what is the B field at any given r distance away? And so hopefully you'll pause and try this, but here I go. If you consider a given loop around this, so this is Ampere's law, the B and the L's are parallel, so B and DL are parallel. So at any given point along this, this loop, which I have attempted to draw in a 3D manner, is parallel with that, so tangent, so the B field is tangent right there with that DL. So they are parallel. So in a sense, we can get rid of that dot product there. And then this integral of DL is essentially saying that what is all of the DLs summed up together, right? So anytime you see an integral, you think summation. And so all of them summed together is simply just the circumference of a circle. So B 2 pi r, right? So some given r distance away, r could be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then epsilon naught and then let's just say an arbitrary I enclosed. And thus the B field, in this case, from Ampere's law, is 2 mu naught I 2 pi r on 2 pi r, right? So hopefully everybody understands that conceptually. So then why is there a need for a correction? And you maybe have noticed that I have this other setup on top, and it's the discussion for the following videos in this series, and that is Ampere's law is simple because it describes the magnetic field from a complete wire. But in this case, what happens if you have a capacitor? Will there be a magnetic field in this direction? And if so, how do we map that? Because there is no current in a conductor, in a capacitor, right? There's no current here. So that's a question that we will discuss in an upcoming video.